Structural dynamics is the study of how a structure responds to an external input, such as a forced excitation or ground motion acceleration. Dynamic parameters, such as modal frequencies and damping constants, are the essential technical information required in engineering analysis and design. Computer modeling alone cannot completely determine the dynamic behavior of structures because of uncertain structural properties, such as damping, nonlinearity, and also boundary conditions. Experimental techniques can be used to determine structural responses for complex structures, like an auditorium. In this video, we are going to show the dynamic response of the Castleman building's lecture auditorium using an impact hammer to excite the structure.
Tests conducted on the auditorium stairs in the center of the room. 5 similar types of accelerometers equally spaced at every other stairs. Beeswax was used to stick the accelerometers to the ground. We choose to perform tests with an impact hammer because it is most cost and time effective. A piezoelectric impact hammer was employed to excite the structure with a known input force. We employed a National Instrument compact deck with sampling set to 2048 Hz and used an anti-aliasing filter. At each location, impact hammer was struck 10 times. The time history of the impact hammer and accelerometers were saved for post-processing. The time records were used to create multiple averages for spectral processing.
The time history was inspected to determine whether the instrumentation was saturated or clipped. The time history for the first dry point is shown in the picture. It was found that hitting the hammer at the base of the stairs resulted in a saturated drive accelerometer and little response on the farthest accelerometer. The center drive location shows a large measured response at all accelerometer locations. Data at the center drive location was employed for further analysis. The measured coherence between the hammer and accelerometer shown in this figure indicated that the linear response was larger than the noise. After 10 averages, a good transfer function was obtained. The transfer function relates the input force at each frequency to the measured magnitude and phase at the response accelerometers. The structure is lightly damped, with most modes having a critical damping ratio of about 0.05. The transfer function response was selected at each natural frequency to draw the mode shape.
The first mode shows that the stiff floor minimizes the structural response at the first 2 locations. The projection room also impacts the mode shapes. The modes get progressively more complex at higher frequencies. The structure was challenging to measure because the stiff structure minimized response at several locations. We obtained the best measurements by measuring and exciting the structure near the peak of the modes. The coherence shows that we got good linear measurements over our valid frequency ranges, even though the structure was challenging to measure. This testing on the auditorium hall structure effectively illustrated the topics we learned in CE 5151.